March 3rd, 1943. North Atlantic Ocean. Position: 52 degrees north, 45 degrees west. The destroyer HMS Harvester is running hard through a force 8 gale, green water breaking over her bow, the temperature barely above freezing. Below decks, in a cramped compartment barely larger than a pantry, a young rating sits hunched over a set of headphones and a dial that glows faintly orange in the darkness. His name is Donald McIntyre. He is 29 years old, a Royal Naval Reserve Lieutenant Commander, and he is listening to the ocean kill people. The sound coming through his headphones is not dramatic. It is a faint pulse, a rhythmic ping, sent outward from the hull into the black water, and returning, when it strikes something solid, as a ghost of itself. It sounds, some men have said, like throwing a pebble into a still pond if you could hear that pond from a mile away. But tonight, McIntyre knows what that returning ghost means. It means there is a U-boat out there, running deep, trying to disappear into the thermal layers of the Atlantic. And it is failing. What McIntyre is operating is ASTIC, the Anti-Submarine Detection Investigation Committee system, later known to the Americans and the wider world as sonar. It is a piece of British technology so secret, so consequential, and so ruthlessly effective in the hands of men who understood it, that the German Naval High Command, the Kriegsmarine, would eventually circulate descriptions of their most feared operators by name. Donald McIntyre would be one of them. The Kriegsmarine would list him as a priority target. His ship was to be sunk on sight. He had, by that point, already sent 4 German submarines and more than 400 men to the bottom of the Atlantic Ocean. Not with superior firepower, not with radar, not with luck, but with sound. This is the story of how a beam of acoustic energy, and the men who learned to wield it, became the most decisive anti-submarine weapon of the Second World War. To understand what ASTIC meant, you have to understand what was happening to Britain in the early years of the war. Britain is an island. Everything it needed to fight. Oil from the Caribbean, steel, and food from North America, troops and material from across the empire, arrived by sea. In September 1939, that sea was already becoming a killing ground. The German U-boat arm, the U-Bootwaffe, was a relatively modest force at the outbreak of war. Roughly 60 operational submarines, of which perhaps 24 might be at sea at any one time. But they were extraordinarily effective. By the end of 1940, they had sunk more than 4 million tons of Allied shipping. By 1942, that figure had risen so catastrophically that Winston Churchill would later write that the only thing that truly frightened him during the entire war was the U-boat peril. Not the Blitz, not the fall of France, not the threat of invasion. The submarines. The mathematics were brutal. Merchant ships were being sunk faster than they could be built. Each lost vessel represented not just steel and cargo, but trained crews, irreplaceable supplies, and months of industrial effort. By the spring of 1943, in the period historians now call the crisis point of the Battle of the Atlantic, the Allies were losing approximately 60 merchant ships per month. At that rate, the economists calculated Britain had roughly 12 months of viable supply chain remaining. After that, the arithmetic of attrition would do the rest. The existing countermeasures were almost entirely inadequate. Surface vessels patrolling without detection equipment were essentially blind. Aircraft, where available, could spot submarines running on the surface in good visibility, but in North Atlantic weather conditions and in darkness, they were largely useless. Depth charges existed, but dropping depth charges without knowing precisely where a submarine was meant scattering them across thousands of cubic meters of water and hoping. The Admiralty's own internal assessments estimated that without improved detection, the war in the Atlantic was unwinnable. The solution, theoretically, had existed since 1917. It had simply never been made to work well enough. ASDIC was developed at the Admiralty Research Laboratory in Teddington, southwest London, where a team led by physicist Albert Wood had been working on acoustic detection methods since the final years of the First World War. The principle was borrowed from nature. Bats, as Wood and his colleagues noted, navigate by emitting sound pulses and interpreting the returning echoes. The question was whether the ocean, with all its temperature layers, salinity gradients and biological noise, could be made to behave as a medium through which sound could be aimed and interpreted with useful precision. The answer, after years of refinement through the 1920s and 1930s, was yes, but with enormous caveats. An ASDIC set worked by mounting a transducer dome on the hull of a vessel, typically below the waterline at the bow. This dome housed a quartz crystal assembly, the quartz being piezoelectric, meaning it generated an electrical charge when compressed and vibrated when current was passed through it. By pulsing electrical current through the crystal at carefully calibrated frequencies, typically between 14,000 and 22,000 Hz, well above the range of human hearing, the transducer could emit a directional beam of sound energy into the water. The width of this beam was roughly 15 degrees, which meant operators had to sweep it methodically through arcs to cover the water ahead and to the sides of their vessel. When that beam struck a solid object, a submarine hull, a whale, a school of fish, occasionally a thermal layer, some of the sound energy bounced back. The same quartz crystal that had emitted the pulse now received the returning echo, converted it back into electrical current, amplified it, and fed it to the operator's headphones. By measuring the time between transmission and return, and knowing the speed of sound in seawater, approximately 1,500 meters per second, though this varied considerably with temperature and salinity, the system could calculate range with reasonable precision. The bearing was determined by the direction in which the dome was pointing when the echo returned. The dome itself was retractable and could be rotated by a handwheel at the operator's station. Trained operators could hear not just the echo but its quality, the slight Doppler shift that indicated whether a target was moving towards or away from them, the characteristic broadness of a return from a large flat surface compared with the sharper echo of a narrow hull, the way a deep submarine tended to return a slightly attenuated signal compared with one running shallower. The dome housing weighed approximately 800 kilograms and was mounted in a flooded recess in the hull, protruding perhaps 60 centimeters below the keel. At high speed, and above about 15 knots, the water turbulence made the system nearly useless. At patrol speeds, between 8 and 12 knots, it was, in skilled hands, devastating. The equipment was manufactured primarily by Submarine Signal Company's British partners and by Metropolitan Vickers in Trafford Park, Manchester, one of the largest electrical engineering facilities in the country. By 1942, sets were being produced at a rate of several hundred per year, with constant incremental improvements to the amplifier circuitry and the dome geometry. Knowing the theory and operating the equipment under combat conditions were two entirely different things. Donald McIntyre had joined the Royal Naval Reserve in 1937, a time when the Navy was still not entirely certain what it would do with ASDIC, even if it worked. He spent the early war years developing what his crewmates called an almost uncanny ability with the system, an ability to distinguish between false contacts and real ones, to maintain contact through the thermal layers that could bend or absorb a sound beam, and to direct his ship for a depth charge attack with what appeared to be a kind of instinct, but was, in reality, thousands of hours of concentrated listening. In March 1941, commanding HMS Walker, McIntyre detected U-100, commanded by Joachim Schepke, one of Germany's most decorated U-boat aces, by ASDIC contact at approximately 2,000 meters. He directed his attack so precisely that Walker's depth charges detonated within 20 meters of U-100's pressure hull, destroying her. He then gained a second contact, U-99, commanded by Otto Kretschmer, the highest-scoring U-boat commander of the entire war, and forced her to the surface with a sustained depth charge pattern. Kretschmer was captured. Schepke was dead. Both actions took place within 2 hours, in the dark, in heavy seas. If you are finding this interesting, a quick subscribe helps more than you know. The psychological impact of ASDIC on U-boat crews was profound and documented in German post-war interrogation records. The ping, that steady, rhythmic transmission that operators could sometimes hear through their own hulls, became a source of dread. Former U-boat crew described lying still in their bunks at silent running depth, listening to the sound growing louder, knowing that an operator above them was tightening the range. Several veterans described the particular horror of hearing the ping suddenly stop, which could mean contact had been lost, or could mean a destroyer was already making her attack run and had switched to passive listening. There was no way to know which. How does ASDIC compare with what Germany and America were deploying at the same period?
Germany had its own acoustic detection technology a passive system called GHG, Gruppenhochgerät, which listened rather than transmitted. It was, in some respects, technically sophisticated, an array of 24 hydrophones arranged in a horseshoe formation around the bow of the submarine, capable of detecting engine noise at considerable range. But passive listening required that the target make noise and, crucially, gave no range information, only bearing. A surface destroyer running at low power in fog could be essentially invisible to GHG until it was very close indeed. Against ASDIC, German submarines had little active countermeasure until quite late in the war. The United States Navy adopted sonar, effectively the American designation for the same underlying technology, though with some distinct engineering differences in the transducer assemblies, from 1942 onwards, largely on the basis of technical exchanges with the Royal Navy. American sets tended to have slightly wider beam angles, which reduced angular precision but made initial detection easier in the vast Pacific search areas. British ASDIC, operated by trained specialists, maintained narrower beams and tended to produce more accurate range and bearing data, which was critical in the tight convoy escort geometry of the Atlantic. American forces themselves acknowledged, in several official assessments produced during and after the war, that British operators had developed operational techniques that American training had not yet replicated. Germany made several attempts to develop decoys and countermeasures. The Pillenwerfer, literally pill thrower, was a calcium hydride cartridge ejected from a torpedo tube that dissolved in seawater and produced a bubble cloud designed to return a false ASDIC echo. It worked to an extent in flat water. In the North Atlantic, with the temperature layers and turbulence already producing numerous false echoes, experienced operators quickly learned to distinguish the sharper, slightly too perfect return of a Pillenwerfer cloud from the duller broadside echo of an actual hull. McIntyre, in his own post-war writings, described learning to recognize it within weeks of Germany's deploying it operationally. The statistical impact of ASDIC on the Battle of the Atlantic is difficult to overstate, but must be contextualized carefully. The technology alone did not win the battle. U-boat losses remained modest through 1941 and into 1942, not because ASDIC failed to detect submarines, but because there were not enough escort vessels equipped with it. In the period known as the Happy Time, Die glückliche Zeit as German crews called it, U-boats were operating in the mid-Atlantic Gap, beyond the range of land-based air cover and in areas where convoy escort was thin or absent. ASDIC could not help ships that were not there. The transformation came in the late spring of 1943, the combination of increasing numbers of ASDIC-equipped escorts, the introduction of very long-range aircraft to close the air gap, improvements in high-frequency direction finding to locate submarines by their radio transmissions, and the intelligence flowing from Bletchley Park's work on the Enigma cipher converged in what historians now sometimes call the turning point of the entire naval war. In May 1943, the Kriegsmarine lost 41 U-boats in a single month. Admiral Karl Dönitz, commanding the U-Boot-Waffe, temporarily withdrew his submarines from the North Atlantic entirely. They returned, but they never again came close to breaking the convoy routes. ASDIC was not the only factor, but it was the sensor without which none of the others could function. You could not attack what you could not find. The legacy of ASDIC extends well beyond the Second World War. The core principle, piezoelectric transducers generating directional acoustic pulses, with echo timing used to determine range and bearing, is the direct ancestor of every modern sonar system, from the bow-mounted spherical arrays of nuclear submarines to the hull-mounted systems of surface warships, to the towed array sonars that trailed behind NATO vessels throughout the Cold War. The specific innovations in signal processing, in transducer geometry, and in the training methods developed by the Royal Navy between 1939 and 1945 form the technical and doctrinal foundation of underwater warfare for the next half-century. An original ASDIC set, Type 144, the standard fit for destroyers and frigates from 1942 onwards, can be examined at the National Museum of the Royal Navy in Portsmouth, mounted alongside the depth charge racks and the plotting tables that turned its outputs into attack solutions. It is a surprisingly modest-looking piece of equipment, a metal cabinet roughly the size of a wardrobe, with a handwheel, a headphone socket, a bearing ring calibrated in degrees, and a small oscilloscope screen. Nothing about it suggests the capacity to find a man-made object the size of a terraced house at a depth of 200 meters in total darkness in a moving sea, and to guide 500 kilograms of high explosive to within lethal proximity of it. But that is consistently what it did. March 3, 1943. The gale is still running and HMS Harvester is still pressing through it. McIntyre is still at his set. The ping goes out, and it comes back, and it comes back wrong. The Doppler return is shifting, the range is closing, the bearing is creeping left. He knows this geometry. He has been here before. He passes the bearing to the bridge. The captain alters course. The depth charge crews move to their stations. What happens in the next 4 minutes will kill 47 men. They are German sailors, most of them in their early 20s, some of them on their first patrol, lying in a steel tube at 140 meters in water so cold it would kill a man in 11 minutes. They do not know they have been found. They cannot see the ship above them. They cannot see anything. They are inside the ocean, and the ocean has given them away. The charges go over the stern and the sides. They sink at approximately 3 meters per second. At the set depth, their hydrostatic pistols fire. The concussion, each charge containing approximately 170 kilograms of Torpex, a mixture roughly 50% more powerful than TNT, travels through the water faster than the human body can perceive it. At 20 meters from the hull, it begins to deform the pressure casing. At 10 meters, it ruptures it. This is what ASDIC made possible. Not merely the finding of submarines, but the translation of sound into geometry, geometry into position, position into consequence. A technology that worked by listening, by casting a thread of acoustic energy into the darkness and waiting for the darkness to answer, and that answered in turn with the most absolute finality available to naval warfare. Donald McIntyre survived the war. He was awarded the Distinguished Service Order 3 times. He wrote 2 books about the Battle of the Atlantic, both of which remain in print. He died in 1981. The U-boats he sank have been on the floor of the North Atlantic for more than 80 years. They are still there. The ocean, having answered, did not give them back.